Okay, good morning, good afternoon, good evening. Thank you very much for attending. Welcome to this GRAS Sound and Vibration and Audio Precision webinar. Today we will be talking about the complicated and challenging, but also interesting world of acoustical tests of laptops and tablets. My name is Santiago Raches. I'm support and application engineer for GRAS Sound and Vibration and Audio Precision. I am located close to Copenhagen in Denmark. And here you can see my contact information. So as you can see, I have two emails, and this is because GRAS and Audio Precision, now they are working together as sister companies under the umbrella of this group that is called the Axiometrics Solutions. Now, in regards to the webinar, today I will have Ole Theilgaard, the director of the Technical Support Department for GRAS Sound and Vibration and AP, helping me answering the questions that you write in the Q&A section. Another thing is that your microphones will be muted. And of course, the recording will be available, and we'll share this recording with you in the next couple of days. As you can see, we have a pretty long agenda for today. So if we don't get to answer all the questions by the end of the webinar, I will still reply to all of you via email. The idea of this webinar is to have a general overview of everything laptop and tablet test related, rather than focusing on a single specific thing. But of course, you're welcome to contact us if you're looking for more specific information about something in particular. So today, first of all, we'll have an overview of the topic and why it's important to perform these tests. We will take a look at the parameters we'll need to measure, the challenges related to the testing. I will show you some GRAS and audio precision equipment that is typically used for this application. We'll talk about open loop testing that is very important, again, for this application. And then we'll show you how to test the internal loudspeakers and internal microphones of the laptops and tablets. Another important thing is that I will show you, we'll talk about actually about noise measurements and other types of tests that we can do here. So first of all, we need to evaluate why do we have a need to discuss this topic, and why is there a need to perform these tests at all, right? It wasn't that long ago that talking about noise measurements or sound quality of computers in general was not even considered by the manufacturers. So when it comes to PCs and laptops, we can say that everything started with noise complaints from the users, actually. The devices were typically making a lot of noise. This could be fan noise, it could be hard drive noise, it could be CD players noise, some things that are not that common nowadays. Anyway, noise from PCs or laptops was disturbing people at home or at the office, and engineers and manufacturers slowly started to take notice of this problem. So we can say that the main reason we started talking about acoustic measurements in computers at all was because of the noise generated by these devices, rather than the sound quality or any other things. So we have to discuss what to measure. What is creating the noise, and therefore what are we exactly measuring? First of all, we need to make a clarification, because today we will concentrate on acoustic measurements. That is when we have microphones and loudspeakers involved in the test, but we'll also be talking about finished products like we see over here. That means that we will not talk about the separate test of a micro speaker or a digital MEMS microphone, even though that is possible to do with audio precision and GRAS products. Okay, so now that that is clear, first we have to make a distinction between noise tests that we see over here and sound quality tests. When it comes to noise testing, we'll find multiple elements in laptops that will contribute to noise generation. In most cases, tablets will lack many of these components or these elements. So for example, we could be referring to fan noise, which includes fan bearing noise, includes vibration from the fan itself. It includes the airflow noise caused by the ventilation system, or it could be the vortex effect from the fan blade edges. Of course, some may argue that we can now find a lot of fanless laptops, but there are still many laptops with processors that require a fan, especially when it comes to laptops for gaming or for video editing. And it will probably be like this for many years to come. Then we have power supply noise. This is also a common issue. It could be related to the noise generated by the electrical coils or the transformers in the power supply that can generate electrical whine. Electrical whine is a high-pitched noise that can be very annoying for the users and people around the device. It could also be keyboard noise, or it could be hard drive noise, even though it's less common to find hard drives nowadays. Or we can even be talking about sound power measurements. On the other hand, when we talk about sound quality, this is like a new application that requires acoustical tests. So for example, we would like that the internal loudspeakers of our device make really good sound for listening to music or for gaming or just watching movies, for example. So for many years, laptops and tablets were equipped with internal loudspeakers of very poor performance. But nowadays, or at least with more expensive devices, it is expected that the product will sound good. So we can say that the sound quality of the product is directly connected to the perceived quality of the product, right? Now, when it comes to sound quality, it's also important to note that when I say sound quality, I'm not necessarily talking about psychoacoustic parameters that are used to describe the performance of a device, but I'm also talking about the objective parameters that we use to test the performance of loudspeakers or microphones. It could be, for example, the frequency response of a loudspeaker, it could be the THD, or it could be the sensitivity of the microphone. Another important thing to consider is video conferencing and all the audio calls performed through laptops and tablets. This has become part of daily lives, especially now during the pandemic. And this is why the performance of the internal microphone or microphones is key for a good video or audio call experience. And then again, an expensive device is expected to have a good performing microphones. And here, last but not least, we can talk about DSP. This is digital signal processing that plays a big role in improving the performance of internal microphones and loudspeakers. For example, sound enhancement features are used for optimizing the sound reproduction for movies, for gaming, for calls, or music listening. On the other hand, we have active noise canceling, or ANC. These algorithms are used to process the sound picked up by the microphone to remove background noise from the audio recorded signal. And we could also talk about electronic audio performance of a sound card, of a digital to analog converter, of an internal amplifier. But as these are not acoustical tests, sorry, we are not going to include this part on this webinar. Anyway, as we can see, laptops and tablets are packed with acoustic devices, such as microphones for calls, microphones for noise reduction, front speakers, bottom speakers, and even sometimes subwoofers. And the performance of these acoustic devices will greatly affect the user experience, and therefore the acoustical testing of laptops and tablets becomes very relevant. I would like to come back for a second to noise testing. So in the last couple of years, we can definitely tell that this new tendency where silence is now a saleable feature. So not only for laptops, of course, but many devices within consumer electronics. It could be a dishwasher, it could be a washing machine, a refrigerator, or whatever. But of course, today we will focus on laptops and tablets. So we can say that silence is now a luxury. We really don't want our devices to make any unwanted noise, neither at work nor at home. I want my laptop to be quiet. So today, we can say that terms such as sound quality or terms like low noise are now marketable terms that are used by marketing teams around the world trying to sell these devices. But now it's also time to talk about noise control laws, noise control regulations. And I can say they are particularly important, at least in Europe where I live. So for example, consumer electronics devices such as computers, they have to go through noise measurement tests for certification. An example of this is a new machinery directive 2006-42 EC from the European Union. This directive has a section about noise control saying that the noise of the device should be assessed in a way that is comparable with devices of the same category. Another example could be the Swedish noise standard, the Stats Control 266. This is from 2004. And it's basically talking about noise emission requirements in terms of guaranteed sound power levels for a variety of IT equipment that includes, of course, laptops or PCs. So these are just some examples of noise control legislation that are being replicated more and more, of course, in different ways, but all around the globe. And this is why we have to pay attention to this. So now I would like to talk about challenges. Challenges, of course, related to this type of tests with laptops and tablets. And for that, I decided to divide the challenges into two categories. First of all, the challenges related to the test itself. And the second category would be the challenges related to the test setup. So we'll talk about first about the test itself. We can say that there is a lack of standardization for some of these tests we will be describing. Actually, the standards available are mostly focused on noise testing only. But for example, there's nothing related to the sound quality performance of internal loudspeakers. And talking about standards, the ones that refer to noise measurements, they usually don't incorporate, or sometimes they do it very vaguely, psychoacoustic parameters to measure to these measurement procedures. And this is particularly important when we want to assess the annoyance that the noise generated by a laptop is creating to a human subject. It's important to remember that our ears are not FFT analyzers or sound level meters, and therefore adding psychoacoustic sound quality parameters to the noise testing can be something that is valuable. So even though standards do exist for measuring and reporting noise data, sometimes the manufacturers don't even make these reports. Or when they do, they might do a poor job in properly making these reports. An example could be when the sound power test is missing, or when they do testing of sound pressure levels, but without indicating the test conditions, such as the distance between the microphone and the device under test. Now let's talk about open loop testing, because this is another challenge. In most cases, these tests with tablets and laptops will require open loop testing. And the open loop test is when the audio signal is not passing through the device under test and analyzed in a continuous operation. We'll discuss this later during this webinar. Another challenge is the different operation modes. because the different operation modes of the DUT might result in completely different test results. An example could be when we are performing fan noise test of a laptop. We have to consider that operating the laptop in idle mode or under heavy load will change the fan performance and therefore will modify the acoustic performance of the laptop. So this is something we need to consider. Another thing is that the standards are usually providing test setups under laboratory conditions. And this is typically a good thing, especially when it comes to performing realistic and repeatable testing. But it could be a problem whenever we want to perform a rapid and streamlined testing for situations such as production line testing, of course. This is why we will discuss some other measurements techniques to tackle this topic. Finally, in acoustic testing of laptops and tablets, sometimes we'll need to use a trained human listener. Sometimes this is essential, and this is true for some situations, especially when it comes to, for example, tuning the internal speakers and sound enhancement algorithms. The good thing is that we can always set up a bunch of golden devices with a trained listener and then use these devices as reference for the production and tuning of other devices. So now let's talk about the test setup challenges. And this is pretty straightforward. And the main challenges are related to selecting the right microphone, selecting the correct sound source, using the correct reference signal for the type of test, and of course, trying to find an adequate test environment like an anechoic chamber or a hemi-anechoic chamber or a test box or something like that. And now I will talk briefly about some of the standards that are available for this testing. So these first three ISO standards are part of a family of standards that are used for noise measurements and noise declaration. The ISO 7779, that is based on the ECMA 74 standard, specifies procedures for measuring and reporting the noise emission of information technology and telecommunications equipment. And of course, this includes devices such as PCs, laptops, and tablets. The basic emission quantity that this standard is using is the A-weighted sound power level. And this sound power level can be used for comparing equipment of the same type, but from different manufacturers. This A-weighted sound power level from the first standard is supplemented by the A-weighted emission sound pressure level in the ISO 11201 standard. And then we have the ISO 9296. This standard, the 9296, is intended for noise declaration. So it's basically taking the raw data from the ISO 7779 and the 11201, and then it's making a mathematical correction of this raw data, and it corrects for the uncertainty in both the measurement and the production of the device. So you will typically end up with a level that is a bit higher than what it was actually measured. Then we have this last standard, the IEEE 1329, that is basically providing the means of checking the operational characteristics of a speakerphone under normal operation. And you may ask, how is this related to the topic of the webinar today? Well, the thing is that this standard has inspired many test engineers to use the proposed test setups of the standard to test other devices that are closely related to speakerphones, devices such as smart speakers, laptops, and tablets. So in all these cases, what we can see is that these standards, even though they are at least these first three that are only related to noise measurements, but all the standards I just mentioned and are providing us with valuable setup descriptions that can be used, and they are actually used quite a lot in the industry, for testing laptops and tablet loudspeakers and microphone performance in a repeatable way. So to continue, we will talk about the test equipment. Actually, selecting the right measurement equipment is as important as having the right setup. So for example, we will need to select measurement microphones like the ones we see over here. We might need a mouth simulator like the one we see over here that we can use as a sound source. We might use a head and torso simulator. In the case of GRAS, we have the KEMAR that can be equipped with a mouth simulator inside the head, but it also can be used as a binaural microphone phones or ear simulators in the ear positions. Of course, we can refer to low noise microphones that are very high sensitive microphones used to capture very weak signals. And we have to talk about the test environment, that it could be an anechoic or a hemi-anechoic chamber like the one we see here in the picture, or a test box typically used in production line testing. And last but not least, of course, we always need an analyzer and a software to analyze all the signals we are measuring, of course. So here we can see 3 different measurement microphones. They are made by GRAS Sound and Vibration. These 3 microphones are typically used for the application we are discussing today. For the ones that are not familiar with the concept, a measurement microphone is an acoustic sensor that is based on a condenser microphone capsule, and it is built according to the Ieee 61094 standard we see over here. These microphones, or measurement microphones in general, are optimized to have a flat frequency response in a particular sound field. They typically have a dynamic range of around 120 dB, and something that is very important is that these sensors can be calibrated according to references that are globally traceable. So measurement microphones are reliable measurement tools that have a long-term stability for the frequency response and also for the sensitivity. And if we check most standards that are referring to acoustic measurements, these standards will typically refer to measurement microphones for capturing acoustic signals. In this case, we have a single half-inch free-field microphone. Then we have a quarter-inch free-field microphone. And here we have a quarter-inch pressure microphone. The free-field microphone, these 2 microphones over here, are optimized to have a flat frequency response when they are used under a free field or close to free field condition. That could be in an anechoic or a hemi-anechoic chamber. While the pressure microphone, like we see over here, is typically used and optimized to have a flat frequency response when placed in small closed cavities, such as couplers or ear simulators, or also when it's flush mounted to a wall or a surface. It is also used when we have to place the microphone very close to the sound source in the near field of a loudspeaker, for example. The half-inch microphones, like the first one we see over here, the GRAS 46AE, has a bigger diaphragm. This bigger diaphragm is loose compared to a quarter-inch microphone. The quarter-inch microphone, on the other hand, will have a small and very tight diaphragm. And the tighter the diaphragm, the more difficult will be to move this diaphragm. And this is why smaller quarter-inch microphones have lower sensitivities compared to a bigger half-inch microphone. We can see here the half-inch microphone has a 50 millivolt per Pascal sensitivity, while the quarter-inch microphone has an 18 millivolt per Pascal or 3.6 millivolt per Pascal sensitivity. So the lower the sensitivity, the higher the noise floor of the microphone. And this is not good, of course. And we can see it here. The quarter-inch microphone have a higher noise floor than a half-inch microphone. But a good thing is that the lower the sensitivity, also the higher the sound pressure levels that we will be able to measure. And this is something good. So it's typically a trade-off decision. Of course, it is usually recommended that the noise floor of the microphone that we are using for the test is 10 dB below the signal we are trying to measure. Another important element of the signal chain for this test is the mouth simulator. And the mouth simulator is basically a sound source with a loudspeaker inside. This loudspeaker is placed inside this very particularly looking metal enclosure, as we see over here in these pictures. And it is used to simulate the diffraction and the acoustical field that is very close to a human mouth. GRAS is offering two different types of mouth simulator, the 44AA and the 44AB. The only difference between them is that one has a built-in amplifier and the other one doesn't have it. We also offer at GRAS head and torso simulator, the KEMAR, that can also be equipped with a mouth simulator, and therefore it can also be used as a sound source. So many consumer electronic standards, like the IEEE 1329, for example, that we just mentioned, refer to a mouth simulator when a sound source is needed. The good thing is that mouth simulators are built according to a standard, and this is the famous ITU-T P51 standard. We can also find them mentioned in these other two IEEE standards, like the 269 or the very old 661 standard. So this means that no matter the brand of the mouth simulators, they are made according to this specific standard, and therefore they are expected to perform in a similar way. Of course, we still need to consider that a mouth simulator is still using a loudspeaker. And loudspeakers have certain tolerances for the frequency response, which means that we can't find a loudspeaker with a perfectly flat frequency response, especially not with this form factor and this very small opening that we have here. And this means that there will be some variation from unit to unit. And this is why it's necessary to equalize the frequency response of the mouth simulator before performing our tests. So this way, the frequency response of the mouth simulator won't affect the test results. And here we can see a typical frequency response of a mouth simulator. The good thing is that the mouth simulator can be quickly equalized with a software like the provided by Audio Precision, using the following process. First of all, we measure the frequency response, and then we export this relative frequency response. Then we import it back to the software, and when we do that, we invert it and we use it as an EQ for the output channel of the mouth that is used with the mouth simulator. And therefore, when we perform the test again, we can see that the final response is a completely flat frequency response. And this is when we are ready for measuring after equalizing the mouth simulator. So let's talk about now about acoustic test boxes. And this is one provided by GRAS. It's called the A30 Test Box. And it is basically an anechoic test chamber, a small anechoic test chamber for acoustic production line testing of mobile devices. So it could be used for mobile phones, it could be used for Bluetooth speakers, but it could also be used for tablets. And that's what I'm showing this device and this webinar, because it can use, it's perfect for testing small and medium-sized tablets. The A30 is a test chamber that is mostly intended for production line testing, but also it is used for fast checking of devices during the R&D process. And here we can see some nice pictures of the A30. It has a big opening in the back that we can use to easily access the test chamber. So we can mount microphones like we see over here, or we can mount a sound source like a mouth simulator. In the front, it has a drawer. And when we open the drawer, we can see that we have telescopic arms where we can place device under test holders. These holders can have different form factors to perfectly accommodate the shape and size of the device that we are testing. And on the side, we can see that we have a connector panel. This panel can be customized with different types of connectors, and it is used to interface whatever element is inside the AL30 with the analyzer or data acquisition system placed outside the test box. The AL30 is basically built to provide a decent self-insertion loss, so we can avoid the background noise in the room affecting the quality of our measurements. Here we can see the self-insertion loss for the AL30. I think it's important to talk about test boxes for this webinar. We did mention before some standards today provide great recommendation for test setups for laptops and tablets. However, these standards don't provide a quick and easy method for testing or a method that is adequate for production line testing. So the way these test chambers are used is the following. First of all, we select a golden device. This could be a tablet or laptop that after proper testing in a hemianechoic chamber or with a trained listener, we all agree that is performing in the way we want. Once we do that, we grab this device, this golden device, and we place it inside the test box and perform the required acoustical tests. Of course, this acoustical test inside the chamber might look a bit different than the test that we performed before in an anechoic chamber. And this is because inside the test box, we have a non-ideal acoustical environment conditions. But that doesn't matter here, as we already know what is the precise performance of that device from the measurements we performed before in the laboratory test. What is actually important here is that we can get repeatable results. This way, we can compare the performance of all the other devices against the curves and results obtained with the golden reference device. And this chart on the right is showing 10 consecutive frequency response measurements of a small tablet's loudspeaker measured with a single microphone inside the chamber. As we can see, this test setup is providing with an easy way to perform repeatable measurements on this kind of devices. So now it's time to talk about audio precision analyzers. We call them the APX analyzers. And APX analyzers, as you can see in these pictures over here, are coming in a large range of configurations, sometimes with more or less analog outputs and inputs, with or without digital inputs and outputs, with different performance in regards to the noise floor or the signal generator specifications. But all these analyzers you can see here are running exactly the same software that we call it the APX 500 software. But today, I want to concentrate on this device we see over here, that is the latest addition to the audio precision family of analyzers, and it's called the APX 517 audio analyzer. This analyzer is specifically designed, configured, and priced to meet production line testing needs. But thanks to all the great features that it has packed in the same box, it is commonly used in R&D testing as well, and for acoustic testing in general. And here we can see some of the features that make the AP17 a perfect solution for acoustic test. First of all, we have a 35 watt audio amplifier that we can use to power any sound source like a mouth simulator. Then we have 2-channel microphone analog input that we see over here. These analog inputs for microphone, they come equipped with power supplies. It could be CCP IEP, but also plus 48 volt phantom power. So we can provide the supply for our measurement microphones without the need of having any other external equipment. The device is also TEDS compatible, so we can use TEDS in the measurement microphones to quickly calibrate the measurement channel. We also have a 2-channel headphone amplifier that we see here. If we happen to want to make headphone testing, it's going to be perfect. Otherwise, it can just be used as another analog output. And then we have the digital I/O module. This is not relevant for this webinar, but we have to consider that having a digital I/O module is very valuable, and this can be configured in many different ways. We can have, as we see here, with a Bluetooth input-output module, we can have HDMI audio, we can have AES SPDIF, we can have PDM or digital serial I/O. So these are definitely capabilities that are more than welcome for electronic audio tests of laptops and tablets as well. So we just said that every APX analyzer is equipped with a software that we call the APX 500 measurement software from Audio Precision. So basically, the APX 500 software is an intuitive and easy to use software that comes with a large number of pre-configured measurements, so you can develop a sequence of measurements very quickly. Then we can generate full tests consisting of many measurement parameters. The software also offers two easy to use modes, the bench mode and the sequence mode. And here we can see the difference between how it looks in the bench mode and the sequence mode. The sequence mode allows users to add defined measurements to a navigation tree and then run this series of measurements in an automated procedure that we call a sequence. And this is very useful in production line testing, for example. On the other hand, we have the bench mode. And in this case, the user gets a configure, a signal generator, an analyzer, a lot of different types of meters, a sweep engine, and a time recorder. So it's basically used for real-time visibility of the device behavior. So we can say more or less that the bench mode is basically the AP software, but without the sequencer. So we can say that the AP software is one of the most advanced audio measurement interfaces available in the market at the moment that allows to use to make very quite complex procedures, including user prompts, measurement limits, as we can see here, some measurement limits. We can call for external applications, and everything can be created directly in the graphical user interface without the need of any programming. But of course, if you like programming, if you like coding, you can also create custom interfaces and application-to-application automation using the included API. And for that, we have extensive documentation and examples that are provided for Visual Basic.NET, C#, MATLAB, LabVIEW, and Python. The important thing is also that you can create these projects, and then you can share it with other APX unit anywhere in the world. So now it's time to talk about open loop testing. The APX software has the capability of running both closed loop or open loop testing. The main difference between testing laptops or tablets, the laptop or tablets audio or normal loudspeakers and microphone is that conventionally you have an uninterrupted signal path from the output to input. But here for laptop and tablet testing, the inputs and outputs are not necessarily directly connected. Actually, in most cases are not directly connected to the analyzer. And this is known as open loop testing. In this particular case, we see here on this slide, we'll be referring to laptops and tablets as playback devices. And this is when we are testing the internal the internal loudspeakers of the laptops and the tablets. So here we basically, this is the basic procedure. We have our device under test. that is a laptop or a tablet. We then configure our signal generator in the APX software, in the computer that is running the software. Then we export the signal as a WAV file, and then we upload this signal into the device under test. In some cases, it might be necessary to encode the signal to, for example, an MP3 file before uploading to the device under test. But if the device under test can playback WAV files, then this step won't be necessary. The next thing is to start the analysis in the computer running the AP software. As the signal was originally created in this computer, in the APX software itself, it has a test, a pilot tone in the beginning. So when we play the signal from the device under test, then the APX analyzer will wait until it hears the pilot tone. And when it hears the pilot tone, it will trigger the signal acquisition. Once we acquire the signal, then we can analyze it. So there are multiple parameters that we can measure when doing acoustical test of the internal loudspeakers of the tablet or a laptop. First of all, of course, the frequency response that is typically considered as the single most important aspect of the performance of any audio device, and this is no exception. We can measure the frequency response of the laptop and tablet loudspeakers with and without the different sound enhancements at the different levels. So we can test, for example, the linearity of the speakers, different SPLs. We can, of course, measure the level generated by the speakers using different test signals. We can we can measure rub and buzz. In the case of the APX, we can measure rub and buzz in many different ways, and you can visit our YouTube channel or our website so you can check all the different ways you can measure rub and buzz. THD or THD plus noise is a very valuable parameter as well. And in the case of a test signal, we will typically use a logarithmic sine sweep. In the AP, we call it chirp, or we can use a fast sweep that is basically a step sine sweep. Here we can see some examples of the test setups based in two different standards mentioned before. We have to remember that these standards were not originally intended to be used in laptop and tablet loudspeaker performance tests, but for noise measurement only. But the setups description that are provided by them is pretty useful and widely used for this type of testing. So the setup on the left is based on the ISO 11201, where the device under test is placed on top of a table. This table is the ISO 7779 table that is specified in the standard. Then the test table is placed inside a hemi-anechoic chamber where we typically have one free field measurement microphone at a position that should be described by the tester. Some laptop designers prefer to use two measurement microphones instead of only one. And when they use two, they separate them at a specified distance from the center to measure both left and the right loudspeakers. On the test of the right, we can see a setup that is based on the IEEE 1329 standard. In this case, the laptop is placed on a test table. This is a different test table. It's an IEEE 1329 test table, and you can find the description of this test table in the standard. This standard also allows for the use of a HATS like the GRAS skimmer that is used as a binaural microphone in this case to capture the signal that is coming from the loudspeakers. Here we can see another setup, in this case for loudspeaker test of tablets. In this case, is based on the ISO 11201. We can use 1 or 2 microphones to perform this test and measure the frequency response of the 1 to 4 internal loudspeakers that are typically found in tablets. As we can see here, the tablet is placed on a tablet stand and is used to simulate the handheld use of the device. Of course, we can repeat all these tests in an acoustic test chamber like the AL30. As we discussed before, production line testing will require the use of a faster and streamlined process rather than a realistic and time-consuming laboratory setup. And therefore, the GRAS AL30 could be a perfect solution for something like this, like a tablet test. And here we can see some pictures of that where we are using 2 quarter-inch measurement microphones, in this case 2 pressure microphones, to measure the response of the loudspeakers that are placed both on the top and on the bottom of the tablet. And then we have a mouth simulator that is used to test the performance of the microphone that we see over here. And now it's time to refer to the laptop or tablet as a playback device. Before, it was a recording device. Now, as a playback device, it means that we will be discussing the open loop procedure for internal test of the microphone or microphones in plural performance test. So in this case, we have to configure the generator. In this case, this is we are going to measure the response of the microphones of the laptop or the tablet. We configure the generator, then we EQ the speaker. We are going to use a mouth simulator for this test, and remember, we have to equalize the mouth simulator so it has a flat frequency response before starting the test. Then we configure the DUT and start the recording. We go to the analyzer, we generate the signal, and then stop recording when the signal is complete. Then we'll transfer the file that is recorded into the PC or tablet to the analyzer, and then we analyze the signal in the APX 500 software. It is important to mention that the APX software allows us to time window the signal if we want to get rid of unwanted reflections, for example, from non-ideal acoustic environments. In the case of the microphone test, we can, of course, again, measure the frequency response, but in this case, it will be the frequency response of the microphone or microphone arrays in the laptop or tablet. We can measure the sensitivity of the microphone just to check that the sensitivity value is still under certain tolerances after the laptop is assembled, for example. We can measure the phase response that is of the microphone or microphones. This is particularly important for microphone arrays that are placed inside laptops and tablets, because these arrays are typically used with beamforming or ANC algorithms to increase the directionality of the array or to reject unwanted background noise from voice calls. Signal to noise ratio is also another useful parameter to measure. And just as we mentioned before, we can use both logarithmic sine sweeps or fast step sweeps for these signals. But we can also use speech signals or music signals. And the APX 500 software can use speech or music signals to obtain a transfer function of the DUT. So this way, we can still perform acoustical measurements in devices that have issues passing sine signals through. And here we can see 2 different setups, one for laptop and one for tablet. They are very similar to the setups I showed before, but in these cases, as we are testing the microphones, we'll be using a mouth simulator to play back the signal generated by the AP software, and that will be captured by the microphone in the laptop or the microphone in the tablet. The same setups or similar setups can be reproduced using the IEEE 1329 standard. In this case, the setup is made in a fully anechoic chamber. We use the ISO 13, the IEEE 1329 table, sorry, for these measurements. And of course, this IEEE standard allows us to use hats also for the measurement, and not only a standalone mouth simulator. And as I mentioned before, we can also perform this test procedure for laptops and tablets inside test chambers for production test. In this case, the microphone inside the chamber could be a quarter-inch microphone if we have problems with space. It can be used for not only for equalizing the mouth simulator, but it could be used, for example, to test the noise floor inside the chamber. So, for example, we can make a sequence in the APX software that measures the noise floor right before we start with the measurement. This way, if we measure a noise level that is higher than X amount, we can warn the operator to avoid performing the test at that moment. Okay, so now it's time to talk about noise tests. So before, we have been discussing sound quality and performance of the loudspeakers and microphone inside laptops. And now we're talking about noise. Here we have a list of possible noise sources that I already showed before, such as fan noise and airflow noise, power supply noise, keyboard noise, hard drive noise, and sound power. Of course, we are not going to discuss every test here today because we don't have time, but you're welcome to contact us so we can discuss the different applications and evaluate the needs of the setups that are specific for all these different types of tests we see here. But anyway, all these noise tests that were mentioned in the previous slides are typically measured using a setup like this one. And this is a setup that is based on the ISO 11201 standard. And this setup is used to measure the noise of the device and the test at the operator's position. The ISO test table is once again used, and we are making this measurement or performing the measurement in a hemi-anechoic chamber. The device under test is placed on top of this test table, and a free field measurement microphone is placed in the operator's position. And this operator position, according to the standard, can be different depending on the device. The important thing is that the specific position that we use has to be reported in the test. The ISO 11201 also allows for the possibility of testing the noise of devices from a bystander position. And this is to see how the noise of a device, such as a laptop, can influence the acoustic environment around the device in a workspace or a home environment. So the test setup, again, is using an ISO 7779 test table to hold the device under test. This measurement is performed inside a hemi-anechoic chamber. And if we want to replicate a test like this, we'll have to use another AP analyzer with more than 2 channels. In this case, we have the APX 526 that has 4 channels. This analyzer doesn't have power supplies for measurement microphones as the APX 517. So in this case, we're using a GRAS 12BB power module, 4-channel power module for powering or for driving the measurement microphones. These measurements have to be made with 4 or more microphone positions that are located 1 meter away from each side of the reference box. This reference box that is delimited by the device and the test. And the height of the microphone is around 1.55 meters above the ground plane. Of course, for more details, you have to refer to this standard. So I already mentioned before low noise microphones. And low noise microphones are also important for these applications, especially when we want to test the noise that is very close to the noise floor of the microphone. Sometimes it is required to measure down to or below the threshold of human hearing. And this is possible by using special high sensitivity microphones that we call low noise microphones, like the 3 we see over here, the GRAS 40HF, the GRAS 47HC, and the GRAS 40HL. Here we can see an example of how and why low noise microphones are useful tools. So on the following charts, we can see measurement results of a signal that is very close to the noise floor of a standard measurement microphone. This could be the measurement of a fan noise from a laptop. It is actually not, but it's a great example. So in the chart on the left, this one we have over here, we have 3 different curves. The orange and the blue curve are representing the signals that are measured by the 2 measurement microphones, the low noise measurement microphone 40HL and the standard measurement microphone GRAS 46AE. The yellow curve, on the other hand, the yellow curve you see over here, is the ISO 226 normal equal loudness contour curve, which here is representing the hearing threshold and the sensitivity of the human hearing system. So this chart on the left is showing us, showing that the low noise microphone is able to measure signals that can be heard by the human, but that the other microphone cannot capture. We can see this in more detail in the chart on the right. Here we can see that we have 2 harmonics, and in the case of the standard microphone that has a higher noise floor, these 2 harmonics are practically masked or masking, or the 2 harmonics are masked by the noise floor of the microphone itself. So we almost cannot measure these harmonics. But in the case of the GRAS 40HL that has a lower noise floor, we can very well see the harmonics and characterize the signal. And talking about low noise microphones, here you can see a lot of them in use, particularly the GRAS 40HH and the GRAS 40HF. These pictures are from the Apple Noise and Vibration Lab that was set up years ago to work on unwanted noise from computers. You can see some. You can read more about this in the source link we have over here. But I think it's important from this picture to note that particularly in the first picture, you can see hints of a setup that is based on the ISO 11201. So we have a hemi-anechoic chamber here, and we have the test, the ISO 7779 test table. On this other case, we can see a similar stand that we use for the tablet testing, in this case inside a fully anechoic chamber. And then in the next setup, we can see a lot of GRAS 40HF low noise microphones that are placed inside of a test chamber. So far we have been talking about the performance of loudspeakers and microphones inside the laptops and tablets. Then we discussed the different methods and parameters to measure related to the noise testing of the different sources in laptops, for example. But we are missing talking about sound and speech quality and intelligibility. We mentioned during the test challenges slide that standards for noise testing usually don't take into account psychoacoustics and sound quality parameters. And I'm not going to get into details here, as this can be a topic for a completely different presentation, and we don't really have much time left. But I think it's important to know that the APX 500 software made by Audio Precision offers the possibility of performing tests such as PESC and Polka. The APX also incorporates the possibility of performing a speech intelligibility test that is following the ABC MRT and the STIPA test, or the STIPA, whatever you call it, test. A test setup example for measurement like this is shown here on the right. We are not going to describe this type of setup now, but you're welcome to contact me if you're interested in exploring a solution like this one. For other sound quality parameters, such as speaker loudness that is described on the ISO 532 standard, it is possible to use third-party tools that are compatible with the APX software to perform this test. We can also see here a GRAS KEYMAR head and torso simulator that can be configured with microphones in the ear canal instead of ear simulators. And this setup is used for sound quality tests. So for example, this way we can record with the KEYMAR noise signals that are coming from a laptop and calculate loudness, or we can record the signals to play back to a jury of human listeners for subjective evaluation of the recorded signals. And this is the last slide. We shouldn't forget about sound power noise testing. Remember, when we started the presentation, we talked about the ISO 7779 standard. This standard is referring to these three ISO standards, 3741, 44, and 45, for sound power testing using a hemisphere kit. GRAS does sell hemisphere kits. We have 1 meter and 2 meter radius hemisphere kits with 4, 10, or 20 channels. Here you can see some examples of the GRAS hemisphere kits in use. In the case of Audio Precision, we do not provide software for sound power measurements, but for an application like this, we can rely on the hardware and software of another company within the Axiometric Solution Group. This company is a German company called IMC Test and Measurement, which is a sister company of GRAS and Audio Precision, and provides the hardware and software that can be used in combination with the GRAS hemisphere kits for the sound power testing. So you are welcome to visit the IMC Test and Measurement website for more information about that. And we are now just in time to finish. This is all for today. I want to thank you very much for attending this presentation. Once again, my name is Santiago Raches. I'm a support and application engineer for GRAS Sound and Vibration and Audio Precision. Here you also have my contact details where you can contact me for anything related to this presentation or anything related to GRAS and Audio Precision.
Find out more at Vicom's website.